Hello and welcome to TidyX episode 176. TidyX is a screencast where we go through and explain how our code works. My name's Ellis Hughes.
And my name's Patrick Ward. Thanks for checking in with us at 176 episodes of TidyX as we chase the elusive 200. As always, be sure to hit like and subscribe on the YouTube channel. Drop the questions, comments down below. We love hearing from you guys, hearing your ideas, questions, things you might be curious about, struggling with, things that you might want us to touch on in future episodes. Drop us a line. As always, we are grateful to all of the listeners. And if you are grateful to us and you'd like to donate to the show, we do have a Patreon page, and we appreciate anything that you'd like to give to the show. We do this out of love. We do it for free. We do it for you guys. So anything that you guys would like to donate, that's awesome. With
Really
that
appreciate
said,
it.
we're going to jump into 176. We're still talking
Yep,
about predicting Hall of Fame pitchers. I feel like we've been on this for a while, and
a
maybe
bit.
we need to start to think about moving off of it. If there's
Let us know
something
what you
you'd
want.
like
Do
to
you want us
see,
to continue to
yeah,
talk about the Hall of Fame pitchers, or do you want us to talk about a different
yeah,
topic?
exactly. If there's something else you'd like us to see, let us know. We're going to jump into episode 176 though. We did some random forest. We've done neural networks, we've done random forest, we've done Bayesian logistic regression, we've done frequent distance, we've done a swath of different models. Today, which is one of the reasons why I love the Bayesian approach, is we got to produce a full distribution of possible probabilities of a player making it to the Hall of Fame, of a pitcher. So it's never
Hmm.
just one single, this guy is 72%. There's always some uncertainty there. Today, we're going to talk about how you can explore that uncertainty with the random forest model that we built last week.
Yep,
And so there's going to be a bunch of data prep and cleanup that happened last week, and then we're going to jump right into 176.
exactly. So we've got our wonderful libraries here: Lawman for the data source, Tidyverse for our data manipulation needs, Broom to view the model results nicely, our sample for helping us do some sampling, metrics, and random forest for our random forest needs. So we've got all that. Then we've got all our data prep. If you want to see how this is done, click the link up above right now, and you can go see how we done it. How we prepared our data set to get all the players post 1970 that have their final decision as to whether they're going to the Hall of Fame or not, which is what we use to train our model, to then be able to predict future players. So I'm going to run all this real quick, because we don't need to go into that right now. If you want to learn more, go watch episode 172. Then we're going to skip over this code real quick, which is training a random forest. We did that in the last episode. Click up now if you want to go see how we trained the random forest and we're evaluating how well it did and how we selected the number of trees we are going to use for the model, or all the other fun bits of creating our model, so we can get to what we're going to talk about today, which is, are you sure? Which player do you think is better, Patrick? How sure are you that that player is actually the better player?
Yeah, fundamental question in science is compared to what? So this is better compared to what? This is worse compared to what? Compared to whom? Compared to which group? And this is not only in science, it's kind of like the most fun part about sports that people argue with is which player is better than the other across eras, etc. So we're going to take our random forest model that we just ran and built. We're going to talk about how to extract out all of the predictions from each of the trees. And then we're going to talk about how you can uh, build some systems to explore the uncertainty across those predictions. And then we're going to wrap this into a nice function that spits out the comparison between two players. It gives us some plots. It gives us some summary tables. So first things first, let's take a look at how we get the predictions out for a single player before we try and do this at scale. So we're just going to grab a player. It's looks like it's going to be John Smoltz. And if we run his data frame, we get all of the data for John Smoltz. Great. That looks perfect. So we've got all of John Smoltz's stuff. If we call predict and we put in type prob, we did this last week. This gives us a matrix of two columns. And column 0 is not making it to the hall, and column 1 is the class of interest, which is making it to the hall. So he's basically a 31-69 split. So high likelihood that this guy is a Hall of Fame pitcher. So where do these probabilities come from? If we were to call predict and we added this argument predict all, watch what happens without even running the individual $ piece yet. If we run this, we get 100 ones and zeros, which come from our our random forest trees. So we had 100 trees, and we get 100 predictions of zeros and ones, yes or no, with each tree making its own unique contribution to the prediction. And you can see that this is a list, and it is demarcated there by that $ individual. So when we call predict, we get that first part, we get that aggregate part, which was what we saw above. If we put $ individual, we're going to get that list element, which is going to be this vector of ones and zeros, and they're all characters. So if we change them to numeric, we get this nice little vector of ones and zeros. And if we took the mean of that, we get the probability of making it to the hall. And obviously 1 minus that probability is the probability of not making it to the hall. Now, this is a binary classifier. So it's a series of ones and zeros. It's not that exciting. If this was a multi-class classifier, like if we had 4 or 5 classes, or if this was a continuous variable, a continuous outcome, it would be much more exciting to look at because we would have much more varied outcomes. And if you want to see how this works with a continuous outcome variable, let us know in the comment section, and we'd be happy to find a data set and go through that.
Or you could provide one.
Or you could provide one. So what we can do, though, with this is we know the probability of making it to the hall is 0.69. So simple math tells us that the standard deviation of a probability, of a proportion, is the probability multiplied by 1 minus the probability. And then we divide that by the sample size, and we take the square root of that whole equation. And that tells us that it's about a 5% standard error on each side of the mean probability of 69%. So we can use some simulation-based approaches to explore this more explicitly. So let's say we do 1,000 simulations, and we're going to use the R-binom function, which is going to take a random draw from a binary variable, ones and zeros. And we're going to ask for 1,000, basically like 1,000 draws of ones of zeros, and we're going to do it 100 times. So 1,000 draws of ones and zeros, where the probability of success should be 0.69. I think when I was doing this,
we had a prior player. Yeah,
I used
or
a different player. And then divide by the number of trees, which is 100, and we get a vector of probabilities. So if we were to run that, we get this nice, cool vector of probabilities. Now we have a huge, we have 1,000 probabilities that we can plot into a histogram, and we can use this to calibrate our uncertainty around the probability that John Smoltz makes it to the Hall of Fame. So we can call some uncertainty intervals using the quantile function, which is basically saying, hey, tell me what the median probability of him making the Hall is, which is 69%. We already know that.
That was
But
set.
then also, what's that?
That was set by our model.
Yeah, that was set. Yeah, we already know that. We explicitly said that. And then tell us what the bottom 2.5% is and the upper 97.5% is. So we want 95% contained within the distribution. Within that distribution we see on the right, that's our 95% uncertainty. So that's pretty cool. What can we do with this? Ellis, want to take us through the next part?
Sure thing. So what we're going to do is we're going to create, add this information into our training data set so we can use this later on. So what we're going to do is we're going to take train, we're going to pipe that into a cbind to then capture the output of predict on train type probability. Again, that's going to give us our probability not getting inducted versus inducted. So we can have those two values in our data set. Then we're going to add the pred Hall of Fame, which is just the binary 1, 0. Are they getting in or not based on our model? Of course, we could just do is it greater than 50% or from the inducted, yeah, in the inducted column. But this is here. Why not? It's we'll be lazy and let it do the work for us. Next thing we're gonna do is we're going to then just take a quick peek at, just for sanity, of what if this looks correct. So we're gonna take train preds, select the player, inducted class, the predicted Hall of Fame, so are they going to get in or not, and then the two probabilities for inducted versus not inducted. Sort it by inducted, so we have the highest probability at the very top, just so that we can, logic check to make sure that this is reasonable. So we've got this player here, 93% inducted, probability. So everybody at the top here that has a high probability was indeed inducted. So logic checks out here. So now we can start comparing, because now we've got all these predictions for all the different players that we've got, and so we can apply all this simulation that Patrick just showed us how to do earlier on, which is just based off of the probability of them getting in, and calculate that for ourselves. So we're going to create a function, and then we can also use those two simulated distributions to compare two different players to try to understand who do we think on average is going to be the better player. Who is, or in this situation, because we're predicting inducted, who on average is more likely to be the inducted player if we're comparing them. You can use this for any use case that you have. Not going to tell you what those are. This is not advice, except for how to code. So what we're going to do is we're going to make a function that lets us do this very easily and very quickly. So if I've got to answer some questions, we're in a bar and I'm like, Patrick, I think this player is better than that player. What do you think?
Yeah.
He
These
can
are things
go,
that people argue about at bars is which players are better than others.
yeah, obviously, all the time. I mean, everyone's got their opinion. So
Yeah.
we can go, yes, but I've got maths on my side. I can tell you, based on a model, who is the better player. So what we're going to do is we're going to call this function pick2. So that's why we're assigning into it. We've got function and three different arguments. Player ID 1, so the player, the actual player ID here for these two players, and then the training set, which is this train preds that we're dropping in here. Mm-hmm. We're going to then, within this function, these are now all going to get run every single time we run this function and print out the results. So the first thing we're going to do is we're going to do set nsims. We're just setting this inside the function. We could make this an argument if we wanted to, but we're just planning on using 10,000 simulations every single time. And the number of trees is 100. Of course, we're just setting this for our purposes because our model was based off of 100. Mm-hmm. We're going to pull out the two players training data sets out of the training set. So we're going to take training set, filter on player ID, and select out their ID, the ER, BB, SO, SV inducted. We're doing this for both players. We can then calculate the difference between the two players, which is the probability of player 1 getting inducted minus the probability of player 2 getting inducted. And from that, we can then derive the standard error difference, which is the probability or the standard error for player 1 minus plus the standard error for player 2.
Yeah, and then take the square root of that. Yep.
Yeah, and then we square root it. We then use the same technique that Patrick showed us earlier, where we do the our binom for n sims, size of the tree, and the probability of both players getting inducted divided by n tree. That gives us the simulations for both player 1 and player 2. We can then use the r norm function, because we assume it's normally distributed, the differences. So again, n sims, mean being the difference between the two players, and the standard deviation being the standard error difference between the two players. Now we can make things nice to help us visualize what's going on here, because numbers, just staring at them is a little like, it's staring at numbers. We all like pretty plots, right? So what we're going to do is I'm going to explain this first plot, and Patrick's going to explain the second plot. So we're first going to initialize to say par mf row 1, 2. So what that's saying is that we want to be able to actually make two plots and plot them right next to each other. So 1 stands for 1 row. So this stands for number of rows. This stands for number of columns. So we're 1 row, 2 columns. The first plot goes into the first slot. The second plot goes into the second slot. We initialize our first plot using the plot function. We're going to, hey, make a density plot of the simulations for player 1. Our line weight is 3. The color will be blue. We're going to manually set the limits of the plot to be from 0 to 1, because otherwise it's going to try to be clever and potentially scale up and down based on the actual data set gets dropped into it, but it's going to be only based on player 1. It's not obviously going to include player 2. So if we have one that has a very low probability and then another player that has a high probability, it could potentially scale that plot up and down. We don't want that, so we're setting the xlim here. Similarly, that's why we're setting our ylim, and then we're going to set the title to be Player Hall of Fame / new line probability comparisons. And so that's going to show up at the top there. We use the lines function to add in the density plot for player number 2. And then just so that we're clear and nobody can be confused which player is which, and so they can't go, when you're arguing with each other, like, see, that one's higher, that one's my player. We're going to add a legend and say, okay, this is going to appear in the top left. The legend is going to have player 1 and then player 2's ID. Set the line weight and the color. So blue, which is the color that we set for the first plot, which is for player 1, and red, which is the color that we put in for the second plot, align with their specific player IDs. So now we can visually kind of compare two different players' simulated probabilities of getting to the Hall of Fame. But Patrick, how else are we going to compare them?
Yep, we're also going to use the difference simulation. So we've calculated that simulated difference between the players using a random draw from a normal distribution. And we're just going to plot that with a histogram. And this could have been a density plot if we wanted, but why not mix things up? So let's use a histogram. Put the difference simulation. Live a little. Put the difference simulation on the x-axis. We're going to just give it a label so that we're explicit. It's the difference between two players, and the X label is the difference in making the Hall of Fame. We're going to fill in the little squares there, or the little rectangles there, with a pale green color. And then we're also going to put an AB line right at 0, since a 0 represents a 0 difference between the two players. And so it's going to be red, line width is going to be 3, and the line type is going to be 2. And after we do that, we figure, you know what? Let's create some output into the console that also gives people information. So we're going to create a stats table where we're going to take the, basically from the start of this function, what we did was we extracted out player 1 and player 2 from the original data set. So we're just going to take their two data sets. We're going to bind them together into rows. We're going to get rid of that inducted column. And then we're going to transpose it. So we're taking it from a horizontal to a vertical, and we're flipping it. And then when you do transpose, there's no row name. So what you want to do is get that first row to be the actual column names, right? So I put row to names using the janitor package, and I want that first row to now be the new column headers. And so I throw it up there.
The player IDs. So now their stats were horizontal, and the first entry were player IDs. By transposing it, now player ID is the first entry, and then all the stats go further down. And so we can just go, and you're now the column names.
And the variables that were in those columns originally in the horizontal, what you'll see is they're going to be the new row names. So this is I use this all the time. It's like a super quick and dirty way, if you have Shiny apps, to just like take a wide data set, spin it up, and then quickly make it look nice and render it as a table. So I use this all the time. We're going to make ours look nice in the console by making a cabal table. So we just call it knitter and the cabal function, and that just gives us some lines and makes things look nice.
It makes it pretty.
Makes it pretty. We also are interested, remember, this episode is about uncertainty. We're interested in the quantile intervals, and we talked about calculating those from the simulations above with the John Smoltz example. We're going to use that exact same approach. We're going to do 95% confidence intervals for player 1 simulation. We're going to do 95% uncertainty intervals there for player 2 simulation. And then we're going to do 95% uncertainty intervals for difference of the simulation. And we're going to put those into a table. And we're going to bind the rows together. We're going to convert it into a data frame. And we're going to set the names as the median, the lower 95, and the upper 95. So that's the lower 95% percentile and the upper 95 percentile. We're going to add in a new column called player. It's going to have the name of, or the ID for player one, the ID for player two. And then we're going to also have the difference, since that was the last part of our simulation. And we could have used the people's table to get their actual player names, but we didn't. Maybe that's a fun exercise for those at home to try.
Yeah. Try it out.
Homework. We're going to relocate that new player column all the way to the front, because it makes sense that it should be at the front, because that's how we're going to read the table from left to right. And then we're going to mutate across everything from median to upper 95%. And let's just round that to 3 digits, because otherwise we get like 10 significant digits and it just looks like a super busy table.
Mm.
The final thing that we're going to do is we're going to make an actual statement. So within the console, we're going to say, we're going to create this true or false value, which is not true or false value, this percentage value, which is how much of the mean difference is greater or equal to 0. So this is the difference simulation. And remember, if it's greater than 0, it means player 1 has a higher chance. And if it's less than 0, it means player 2 has a higher chance of making the haul. So we can make a probabilistic statement here with an if else. We're going to say, if the difference in simulation is greater or equal to 0, then player 1 has and then take that mean difference over 0 and turn it into a percentage with the paste function, has a X% greater chance of making it to the hall over player 2. If the mean difference is not greater or equal to 0, then player 2 has a 1 minus that mean, right? Because we want the inverse, we want the opposite chance of making it to the hall over player 1. So we're just going to make that probabilistic statement, and then we're going to dump everything out into the console in a list.
Quick. I just saw this is the mean diff sim. So this value, if else, is either, wouldn't it be the mean greater than equal to 0?
Oh, there it is.
There we go.
Yeah.
Did I?
And actually, we probably could have just done if diff over 0 is greater than
Yeah.
right. So it was a bit of the same thing. I hastefully coded that. So,
That.
yeah, that works too.
No. No. This. Because
Yes.
if it's greater than 0, if the mean of diff sim is greater than 0,
Yes,
that means
that's
player
it.
1.
Yep.
Yeah.
Yeah, you got it.
This
Yep.
this is I still think correct. This is just a
Yes.
different.
Yes.
These are two different things. And
Correct. Yeah.
then we throw all that into a list.
Lists are awesome for returning function outputs to consoles.
Yes.
I had a new R coder ask me last night, text me like, "Hey, I'm doing this data camp course. Do you ever use lists?" And I'm like all the time. You can store all kinds of outputs in this. Notice that we stored 2 different kinds of tables. We're going to have stored a text string outcome. We could have also done a t-test. If you wanted to do like some sort of formal statistical test on this difference, we could have done a t-test. We could have stored that entire output as part of this list.
We could have all the plots that we just made, if we'd made them as ggplots, we could have saved them as gg objects and put that into the list as well. And it wouldn't, like, lists are so incredibly flexible. If you don't know a ton about lists, let us know. We'll make an episode.
You can do an episode. I use lists all the time. But now the function is ready to go. So let's have at it, huh?
All right. So we've got this first comparison between Hoff MTR01 and Mora JA02. I'm sorry, I'm just awful with player names, so that's how
Probably
I'm
want to rerun it so that because your graphics window is too small there.
Boop.
Maybe. There we go.
There we go. So now we can see here on the left-hand side in our console, we got our stats table. So this is Hoff MTR versus Mora JA. And you can see there is a bit of a difference between the number of runs and strikeouts and whatnot. But Hoff MTR, the saves. Right? I'm reading that right? The saves?
Yeah, yeah.
Then we can also see the higher probability of getting in, median 93 versus 66, with the difference between 27%. And then player 1 has a 100% chance of making the Hall of Fame over player 2. So based on our simulations.
Yeah, and this isn't saying that player 2 won't make the Hall of Fame. It's just saying comparatively to player 1. And we can see that player 2 with 601 saves was more of a relief pitcher, which in our first episode in our exploratory data analysis, we learned how hard it is for just relief pitchers to make it alone. It's hard enough for a pitcher to make it, but to be a reliever, really hard to make it. So
Yeah.
kind of works out. Let's pick two players that are a little closer together in their chances. So we have
So
Dennis Eckersley and Pedro Martinez. Okay, so these guys overlap a little bit more. They're a much closer together. 3% difference between them. We can see the two distributions there. We have the difference between the two players. So we can see that there's a larger amount of the probability mass is centered to the right in favor of player 1, which in this case is Dennis Eckersley. Again, we could have done some more formal testing and dumped that into the list. We could have done a t-test. We could have actually mathematically computed the integral of the overlap between the red and blue distributions. We could have done different things here. This was just a simple list outcome, but there again, if you want to know more about the things you can do with lists and all the things you can put in there, let us know in the comments section. But overall, really quickly, in about 20 or 25 minutes, we've created a cool little player compare function that allows us to dump results out into graphics and the console. And if you really wanted to get creative here, you could grab that entire function and put it into a Shiny app and run it, and you would get this output. You can select any players you want without having to type anything, and it'd be pretty
yep.
cool.
Yeah. Do all the fun things and make it all interactive
The
and
fun
bring
things.
joy to your world.
Totally.
All
Totally.
right, with that, that is episode 176 of TidyX. Are you sure? As always, my name's Ellis Hughes. You can find me on various social media sites at Ellis_Hughes.
And my name is Patrick Ward. You can find me on X at OSP Patrick at tidy_explained is where you can find the both of us tweeting from the screencast. Of course, easiest way to get in touch with us though is the YouTube channel. Comments, questions down below, what you'd like to see, what you'd like help with. And we do have a Patreon page if you'd like to donate to the show. We're appreciative of anything that you would like to give.
Thank you all so much and keep on exploring your world.